I keep getting dinged by my 5-minute limit. So I was talking about the charge conservation in positron emission radiation. If your proton changes to a neutron, in order for charge to be conserved, you have to still have a positive charge. So a positively charged anti-electron, aka positron, is emitted, just as the negatively charged electron is emitted in beta decay to conserve charge of a neutron turning into a proton. So here the redistribution of energy and mass and all that stuff causes the release of a neutrino and a gamma ray, a high energy photon. In positron emission, you have changed a proton to a neutron. So your mass number hasn't changed, but your atomic number has decreased by 1. I think this official slide is wrong. We're not really worried right now about those details, just in the idea that the positron emission and beta decay are real similar. They're real similar, like subatomic processes, once you understand the functioning of quarks, like the interrelationship between quarks. So all that said, radioactive elements often go through a series of successive decays until they form a stable nucleus, right? We said that at the beginning. If you've got an unstable nucleus, it's going to shed stuff, change stuff, try to reach a more stable energy level configuration of protons and neutrons, so that strong nuclear force hooks everybody together. Here's a summary of the 3 types of radiation. Again, we don't need to memorize or know these features except to understand that radiation is a natural process, that it's sort of the result of an atomic nucleus seeking a more stable configuration, and that particles are ejected in this process. So the last little bit about radiation includes some information about fission and fusion. We don't need to understand fission or fusion to proceed with our cloud chamber experiment, but it's an interesting continuation of the thought process. So nuclear fission, in my mind, is really similar to alpha decay. The only difference is that the nuclear fission is kind of started off by firing a high energy neutron to an already unstable nucleus. So in alpha decay, we had uranium-238, I think, spontaneously decomposing into an alpha particle, which is a helium nucleus, and thorium something or other. In fission, we are firing, for example, a neutron at a uranium-235 nucleus. So firing a neutron at an already unstable nucleus, and that extra neutron sort of destabilizes that atom so much that it can't hold together anymore, and it splits into 2 bigger chunks. So it splits into not a helium nucleus and a thorium, it splits into 2 bigger, almost like more equal pieces. And then as those equal pieces become stable or stabler, they have fewer protons. They don't need as many neutrons to hold themselves together, so they release or eject some neutrons. Those neutrons, in turn, can interact with nearby other unstable nuclei. And that's the result, or what results or can result, is a chain reaction. So you fire a neutron at some uranium, the uranium splits. Those pieces that it split into don't need as many neutrons, so they eject neutrons. Those ejected neutrons interact with some other uranium nuclei, which in turn split. As they split, they eject neutrons. Those ejected neutrons interact with more uranium nuclei, and so on. So we've tried to harness this natural process. Humans have tried to harness this natural fission process in order to heat water to run, to generate steam to run a turbine to generate electrical current for our use. It is a very efficient way to produce current. However, it is not without its problems. So our other option is basically the reverse. Instead of splitting apart big atoms, we join small atom nuclei together to make bigger ones. This is what's happening in the sun. We're smashing because of gravity, mashing them together. We have hydrogen smashing together to become helium. And energy is released, the sun shines. We've also tried